Introduction to heat capacity. Have you ever wondered why water is used as a cooling agent in a car radiator? A lot of heat is generated in a car engine. Water is used in a radiator as a cooling agent because water has a high specific heat capacity. This means that a large amount of heat is required to raise the temperature of 1 kilogram of water by 1 degree Celsius. Click Specific Heat Capacity. In this lesson, you will be able to define heat capacity, specific heat capacity, and molar heat capacity. Use the equation Q equals C times delta theta, Q equals MC times delta theta, and Q equals NCM times delta theta. Understand that CPM and CVM depend on the degrees of freedom. Derive the expression CVM equals F over 2 times R and CPM equals 1 over 2 times F plus 2 times R. Derive and use the equation CPM minus CVM equals R and know that gamma equals CPM over CVM. Click buttons to switch on the heaters. Note the heat required to raise the temperature of the copper blocks from 30.0 degrees Celsius to 40.0 degrees Celsius. What is the relationship between heat required Q and the mass m of copper? Answer: heat required Q is directly proportional to m. Click button to switch on the heater. Note the heat required to raise the temperature of 1 kilogram copper block from 30.0 degrees Celsius to 40.0 degrees Celsius. Click button to switch on the heater. Note the heat required to raise the temperature of 1 kilogram copper block from 30.0 degrees Celsius to 50.0 degrees Celsius. What is the relationship between the heat required Q and the increase in temperature delta theta of the copper block? Answer: heat required Q is directly proportional to delta theta. Click button to switch on the heater. Note the heat required to raise the temperature of 1 kilogram copper block from 30.0 degrees Celsius to 40.0 degrees Celsius. Click button to switch on the heater. Note the heat required to raise the temperature of 1 kilogram aluminum block from 30.0 degrees Celsius to 40.0 degrees Celsius. What do you deduce about Q, the heat required to produce the same increase in temperature for different materials of the same mass? Answer: heat required Q depends on the type of material. The heat required to raise the temperature of a material depends on the following factors. When the temperature of an object rises, it gains heat. When the temperature of an object decreases, it loses heat. The specific heat capacities of three metals are as shown above. Equal volume of boiling water is poured into 3 containers of the same mass and each made of aluminum, copper and iron. Click on each thermometer to read the final equilibrium temperature of the water. Hence, identify the metal of each container. Select your answers. The heat capacity C of a body is the quantity of heat required to raise the temperature of the body by 1 Kelvin. The molar heat capacity of a material, Cm, is the heat required to raise the temperature of 1 mole of the material by 1 Kelvin. The relationship between the molar heat capacity Cm and the specific heat capacity C is as shown. The specific heat capacity of water is 4,200 joule per kilogram per Kelvin. What is the molar heat capacity of water? Summary. The specific heat capacity C of a material is the quantity of heat required to raise the temperature of a unit mass of the material by 1 Kelvin. Specific heat capacity C equals Q over m times delta theta. Unit of C equals joules per kilogram per Kelvin or joules per kilogram per degree Celsius. The heat capacity C of a material is the quantity of heat required to raise the temperature of the material by 1 Kelvin. Heat capacity C equals m times C. Unit of C equals joules per Kelvin or joules per degree Celsius. The molar heat capacity Cm of a material is the quantity of heat required to raise the temperature of a mole of the material by 1 Kelvin. Molar heat capacity Cm equals big M times C. Unit of Cm equals joules per mole per Kelvin or joules per mole per degree Celsius. The heat required to raise the temperature of a gas depends on whether the gas is heated at constant volume or at constant pressure. The molar heat capacity of a gas at constant volume and at constant pressure are defined as follows. Click on the button shown and observe a gas being heated at constant volume. What happens to the kinetic energy of the gas molecules and the temperature of the gas? Answer. The kinetic energy of the gas molecules increases. The internal energy of the gas increases. The temperature of the gas increases. Click on the button shown and observe a gas being heated at constant pressure. What happens to the heat supplied to the gas? Answer. The heat supplied is equal to the sum of the increase in the internal energy of the gas and the work done by the gas during expansion. Compare the heat required to raise the temperature of the gas at constant volume with the heat required to raise its temperature by the same amount at constant pressure. Which process requires more heat? Answer: more heat is required when the gas is heated at constant pressure. Click on constant volume and constant pressure to find out why. Consider 1 mole of ideal gas being heated separately at constant volume and at constant pressure. The relationship between the molar heat capacities at constant volume CVM and at constant pressure CPM can be deduced as follows. The ratio of the principal molar heat capacities of a gas CPM and CVM can be deduced as follows. What are the values of gamma at room temperature for monatomic, diatomic and polyatomic gases? Select the number of degrees of freedom F and the value of gamma for each type of gas by clicking Select. Summary: the relationship between CVM and CPM is given by CPM minus CVM equals R. The ratio of CPM to CVM is denoted by the symbol gamma. Gamma equals CPM over CVM, which implies gamma equals F plus 2 over F. The value of gamma equals CPM over CVM can be used to determine whether a gas is monatomic, diatomic or polyatomic.